All right, well, welcome everybody to Smart Ventilation and Air Distribution. Real quick, a huge thanks to our top tier sponsor, Build Equinox with the Serve 2. The Serve 2 compares itself to ERVs and HRVs, but has many more features that these systems do not include. For the most part, the Serve 2 runs very low in its energy use, and then ramps up when pollution is detected in the air to exhaust the air from your client's home or multifamily unit or commercial office, as opposed to an ERV or HRV, which just runs at high energy all day. The Serve 2 comes with smart control systems to set the thresholds of VOCs and carbon monoxide in the home, carbon dioxide. It comes with a filtered air system up to MERV 13 or even higher for filtering incoming air and recirculation air. It comes with an energy efficient ECM, and it has an integrated heat pump system to help ensure that the air is 100% comfortable. The Serve 2 is manufactured right in Urbana, Illinois, 100% American made, 100% solar powered facility. And it works very well with heat pump water heaters such as the Rheem Prestige. Works very well with a Mitsubishi all-electric heat pump system to help distribute ductless mini-split air heating and cooling around the house. And has the GeoBoost ground loop heat exchanger, which can work very well with geothermal systems such as the GeoComfort geothermal system. So go to buildequinox.com today and check out the Serve 2. All right, well, welcome everyone to Smart Ventilation and Air Distribution. This course is approved for 1 hour in continuing education units, LEED AP Homes, Certified Passive House Consultant, AIBD, Certified Green Professional, Certified Green Home Professional, BPI non-whole house, as well as AIA Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. Today I will be your moderator. My name is Brett Little, and I am the Executive Director here at the nonprofit The Green Home Institute. For this session, we're going to be talking about smarter ways to ventilate and distribute building air. And so I'm very excited to announce our speaker today, Ty Newell. So take it away, Ty. Thank you.
Okay. Good afternoon, everyone. My name's Ty Newell, and I think my screen should be showing. Okay. During the introduction, when Brett had me muted, for some reason my sound also got muted. So I have no idea what he said about me, but that may be for the better in any case. But I think things are running fine now. And as I have trouble walking and chewing gum at the same time, as questions come up, Brett may break in periodically to let me know or ask questions that should be answered at the time. And otherwise, at the end of the talk, for sure we'll answer all the questions that have been coming in. So just briefly, at Build Equinox, I get the pleasure of working with these two young guys, Ben and Alex, and our mission is to figure out how to live in a sustainable manner, how to live on our daily allowance of solar energy. And as I have this quote here from Aldo Leopold, how do we, a simple question, but very complex, as many of you know, how do we live on a piece of land without spoiling it? And our focus as a company is how do we also keep us healthy? How do we keep us well and feeling good? And how do we do that in an unobtrusive manner? And so that's what this talk is about as we discuss the concept of smart ventilation, some of the implications of it, along with smart distribution of air, something that's often a forgotten or neglected aspect of design, but very essential as well for making sure we have a healthy indoor environment. Good. So our objectives here, to discuss smart ventilation, a few ideas about it, although there's a lot of interpretation as this is an evolving, developing field. But more importantly, how does it compare with what tends to be the conventional type of, say, energy recovery ventilation that we're seeing in today's high performance homes and in renovated homes that are being sealed and ventilated? A second topic will be smart air distribution in order to see some of the characteristics that happens within our homes. Maybe we're getting plenty of ventilation air into the home, but if it's not getting to the region of the home where we need it and when we need it, there's a lot of fresh air that's wasted. And as well as the place where we need it, a lot of folks that may be spending a lot of time in poor air quality. And the two aspects of that we feel are essential: recirculation, and then sometimes layered on top of that, zone control. And above all, those of you involved in the building industry, as well as those of you who are homeowners or interested in general, that these decisions we're making as we design a home or renovate a home, it's more than just us and the way we might think we like to live, but we really need to think about a house having good decisions made for the next 100 years, so that, just for example, ductwork, as in a previous webinar, that if it's too small and somebody at a later time has to come in and increase its size for better ventilation, it's a significant cost compared to just putting it in at a decent size to begin with. As far as smart ventilation, and again, this is open to interpretation, but smart ventilation to me means that you're measuring indoor air pollutants. With modern technology, we now have the capability to do that. There's more improvements that need to be added, but these are coming along, and as they come along, we need to implement them. But basically, measure air pollutants and then ventilate whenever any of these get above a desired threshold. And to sense outdoor conditions, because in many places, it's sometimes nicer outdoors than indoors, and equivalent to opening a window when it's nice, to have a smart ventilation system simply and in an automated manner bring in as much fresh air as it can. In addition, to do these things with high energy efficiency while maintaining excellent air quality. And as I hope you'll see through this talk, that you can have your cake and eat it too. But our focus is really on human health and well-being, and we view energy as being important, but as being one of the constraints, not the objective to what our activities revolve around. And to us, it's also important to archive indoor air quality data. So for example, with our systems, someone's data is archived and available to them at any time, so they can sort through and look through their data and hopefully figure out when things are going well for them and when they're not, or what changes they might adjust. As well as in the broader scheme of things, for us to help understand how we might improve algorithms and controls that for the public in general is improving the indoor environmental quality. And then also, even though the technology behind these is beyond most of our expertise, just like the modern car, we generally know how to drive a car in a similar manner within a house. As technologically advanced as cars are becoming, to have a house that makes use of technological advances, but that it uses them in an unobtrusive manner, in a smart manner. Now, smart air distribution And we purposely separate this out, and the handout materials that are available with this webinar, one report is on smart ventilation and the other is on smart air distribution. And we purposely broke this into two because we do feel these are two subjects, and we want smart air distribution to be held with the same importance as ventilation. And it has its own characteristics and aspects that need to be handled. But a smart air distribution system will distribute fresh air where and when it's needed in a home and maintain high air quality throughout. And to do this in an efficient manner. And this efficiency is fresh air efficiency, to make sure that all of the fresh air that's been brought into a home, that it is used to benefit the well-being of the home's occupants. In many homes that are simply once through ventilation, which we'll discuss, 3/4 of the air may move through rooms that haven't seen a human for several hours or several days. And it simply works its way over to the exhaust and is exhausted from the house. And there's an energy efficiency penalty, but also there's a air quality penalty that's paid in these types of systems. Now, one of the foundations of smart air distribution is recirculation. And although you may have the understanding that recirculation should maybe be avoided or isn't so important, we feel it is essential in all homes. Recirculation it's one of the ways to utilize fresh air that's been stored in unoccupied regions. A very important aspect of recirculation is to remove indoor generated particulates, as well as particulates that made it through the outdoor air filter. Most homes now, as we've started seeing homes regularly built with infiltration levels that are below 6 air changes per hour at 50 pascals, the majority of particulates in the home, upwards of 80–90% of the particulates in the home, are indoor generated from skin flakes that fall off of us throughout the year, to cooking particulates, to particulates from dirt brought in on our shoes, and then just abrasion of textiles as we move around or our feet rub on the floor. So recirculation is our opportunity to keep and maintain low particulate concentration levels in our homes. And then recirculation improves comfort. It helps even out comfort throughout a home, from the occupied to the unoccupied areas. When a home gets large and more complex, and we'll talk about this, but it's a simple calculation. But typically, a home getting larger than 2,000 square feet, in which the airflow that we feel is a reasonable airflow for ventilation needs, about 200 cubic feet per minute. As you get above 2,000 square feet, it takes maybe an hour to 2 hours to circulate that volume through the smart ventilation system. And so as you get a home where it might take more than 2 hours, this is getting to where smart zoning comes into play and may be a benefit. Smart ventilation works. There's no question. We're in homes throughout the United States and Canada, and with today's miracle of online data collection, that we are able to see how homes are doing. And in this slide, taken from 34 homes in Vermont, these are Vermont homes, and you may have seen our report on energy, comfort, and indoor air quality on these Vermont homes. But here's 34 homes, the CO2 and VOC average readings over about a 5-month period. The horizontal axis is the set point on the smart ventilation system. And most of these homes, the homeowners set it where they like the air quality, have set it at about 1,000 parts per million of CO2 and equivalent VOCs, and a few greater than that and a few less than that. And then one person who really wants as close to outdoor air as they can get with a setting of 600 parts per million. And over on the vertical scale, you can see what the average CO2 and VOC concentration. The bulk of these homes, VOCs dominates, and this is a characteristic we find in electric homes. Homes with natural gas generally are dominated by CO2, even though natural gas is spewing out a large array of VOCs, unburned hydrocarbons, carbon monoxide, and such, that the CO2 coming out of the combustion generally outweighs the VOCs given off by the cooking odors and unburned gases. In an all-electric home, though, this is typical of what we see. Now you can see that there's one home here around 950 parts per million for the set point that has CO2 higher than VOCs. These VOCs are equivalent VOCs to the amount of VOCs given off by a person relative to their typical CO2 output. And when VOCs are greater than the CO2 output, that's indicating something else, as in most of these data points, something else is added to it. Maybe a cleaner, maybe off-gassing from furnishings, maybe a can of paint that's opened, or cosmetics, or cooking. But when VOCs are lower than CO2, this generally indicates that this is a low polluting household, that the humans are the primary source of the VOC pollutants, which, in addition to smelling bad if they build up too much, also impair and impact your well-being. And but VOCs disappear in more ways than CO2. CO2 needs to be ventilated out. It's not reacting and largely isn't getting absorbed in things. VOCs are reactive compounds, and they're regularly breaking down into hopefully things like water and carbon dioxide, as well as getting absorbed and then sometimes desorbed, but they have other ways to disappear in addition to being diluted. Now, as far as ventilation, this slide shows for a human with what we consider sedentary activity, basically sitting or standing, but about 1.2 metabolic units of activity. You might increase to as much as 9 or 10 metabolic units under heavy exercise, and sleep, you'd be at about 0.7 metabolic units. And the generation of CO2 per person per hour at this 1.2 mets is somewhere around 0.04 kilograms of CO2. And if you put that person in a room and blow, say, 20 CFM of air through that room, you would find that the carbon dioxide concentration would be at about 1,000 parts per million, where this red circle is showing. If you double that to about 40, say 50 CFM per person, much greater than what you typically have from today's ventilation standards, but really what was quite common back in the early part of the 20th century and 19th century, you would find that you would have equivalent to the effectiveness of the flu vaccine, roughly a 35% or so drop in flu and absentee cases due to flus and colds. And so if you're a business owner and you have a lot of employees and you find that you're running at about 1,000 or so ppm of carbon dioxide, crank that ventilation up and you'll have less sick days. And this is quantitatively shown in a very large-scale study. You can download the paper from our website, as well as it's in the attached list of references to this. But basically, fresh air is every bit as effective as the flu vaccine. And the nice thing about fresh air is you don't have to guess what strain of flu is coming in. And for sure, of course, would recommend both to get an even better effectiveness at not transmitting airborne diseases. You also see a fairly broad range if you take the ASHRAE 62.2 ventilation table and then look at the ventilation per person. And this ventilation schedule also has a household size, a house size component, as well as a occupancy component. But this really has a large variation if you just base the ventilation table on the number of occupants. And at the one end, when you're getting above 80 CFM per person, you're very inefficient, bringing in a lot of air that wasn't needed to maintain good health. And when you get down to 10, your house is going to smell. People aren't going to like it. Regarding ASHRAE 62.2, and the committee members readily admit and state in the standard that it's a ventilation standard. It's not an air quality standard. I think they're getting close to where, with today's technology, that they see that they can start changing to an air quality standard. But as a ventilation standard, it's simply based roughly on where 20% of the populace would be dissatisfied with the air quality. And so it's an odor-based threshold. And odor and air quality are two different things. There's lots of things in the air that you will never ever smell that are at a high enough concentration to be unhealthy. And then there's lots of things that you smell that you may not like, but are very, very much not unhealthy. For example, the mercaptan that's injected into natural gas so you can smell it because you can't smell methane. But mercaptan is one of the smelliest substances on earth. You can smell it at a concentration that is very, very far away from it being an unhealthy concentration. So odor is not a good correlation to air quality. And the threshold at which air quality is good generally tends to be below that, where people are just dissatisfied because of odor. There's no specification on air distribution. Nominally, most of the ventilation table results in about 20 CFM per person, which will give you roughly about 1,000 ppm of CO2 and an equivalent level of VOCs. Now, 62.2 since 2013 and now the current 2016 ventilation standard, it allows for smart ventilation. And what they consider smart ventilation is something that is actively or automatically controlling your air quality, and that it will lead to a lower annual exposure to pollutants. This table, which is just using the calculations for the ventilation standard, the 62.2 2016 standard, and we're going to look at a home that's 2,700 square feet with 4 bedrooms, which is the average new US home, quite large, especially given that the average occupancy of a home in the US is 2.5 people. But this home, if it's to follow the ventilation standard, would have about 120 CFM. And so we'll look at how smart ventilation compared to this average home with a high performance HRV, a 90% heat recovery ventilator, compare in energy efficiency as well as air quality. And then we'll look down at this other end, a 1,000 square foot home with 2 bedrooms, which would nominally have about 50 CFM, and get an idea of how its air quality as well as energy performance compare. As far as home exposure, this plot, it shows what we call CO2 hours or CO2 pollutant hours per day on the horizontal scale and VOC pollutant hours per day on the vertical scale. These pollutant hours are similar to kilowatt hours. They're integrated exposures to pollutants. And we define a pollutant hour, basically 1,000 ppm for an hour. So if you're in a room with 1,000 ppm of carbon dioxide for an hour, that would be 1 pollutant hour of exposure. And if you're in that room for 24 hours at 1,000 ppm, that would be 24 pollutant hours for that day. And similarly for VOC hours, if you have the equivalent of the VOCs a human puts out when a human is creating a room with 1,000 ppm of carbon dioxide, you would similarly have 24 hours of VOC pollutant hours per day if that room was at 1,000 ppm generated by human occupancy. This yellow band is where ASHRAE ventilation standards would have you as far as exposure. And the data points on this are from 14 conventional so-called leaky homes. These are homes that would have blower door values above 6, most likely 10 or so air changes per hour. And a number of these 14 homes, this is over about a 2 to 3 week period where we monitored the air quality in these homes. The majority of these homes, or at least half of them, have natural gas. And you'll see that the majority of the pollutant scale on these homes is toward CO2 rather than VOCs. This green area is where we'd like to see homes, less than 24 pollutant hours per day of CO2, VOCs, as well as a combination of the two. And when we look at smart ventilated homes, so here's 10 smart ventilated homes, and this is over January month. These homes are spread across the United States, so they're hitting a variety of regions. And we picked January for this data just because this is when many homes throughout the US would be sealed up. And so a time when they need to actively be managed as far as air quality. But you can see that these homes are much, much more within this green area as far as its exposure. And then because this is January, and it turns out that January 1st of this year that was used, along with January 8th, that these were vacation days and New Year's holidays. And so the pollutant levels that are exceeding the green tended to be on January 1st and 2nd and January 8th and 9th when someone might have visitors or a party or something like that going on. These are all electric homes, and the VOCs tend to be the dominant pollutant as indoor combustion is eliminated. As far as current standards, LEED certification recognizes advanced ventilation technologies, and we'll talk some about these types of sensors, but for sure, these sensors are a part of a smart ventilation system to be able to see what's happening in bathrooms and occupied rooms. And then as far as balanced ventilation, we feel this is very important, that you're bringing air in and exhausting air at nominally the same rate. For those of you that are following the Passive House US standards, and here as far as the 2015, and there's a more recent version that may be out that I haven't read through yet. But FIAS largely follows ASHRAE, so even though they stated in terms of 0.3 air changes per hour, when you look at different size homes with the expected volume of the home, this compares quite well to what ASHRAE would also be proposing for that size home. And for those of you following the International Passive House, I think this is current as I got it off their website, but hopefully they are studying this, and because I know Europe is far ahead of this, that Europe is, many countries in Europe are actively looking at exposure standards for air quality management in homes and buildings. And this statement stating 30 cubic meters per hour per person is something less than 20 CFM per person. And this is in the opposite direction where we'd like to be seeing fresh air going in a home. So at least from my viewpoint, this is too low. And finally, as a little bit of health perspective, the value of our health relative to energy, and why we put health, not only because it's important for people to feel good, but there's a cost associated with feeling good. If all 100 million, 125 million residences in the US were high performance, reasonably well insulated and sealed, we'd be spending about $160 billion per year. We're not there yet for sure, and we have several years to get there through renovation and retrofit and new construction. But we're maybe 2 to 3 times that. So it's not like an excessively high number compared to this 160 billion. We look at the cost of flu and colds, about $130 billion per year. And if we increase the level of ventilation and knock off maybe 30% of that, that's a giant chunk achieved without increased energy costs, and simply by eliminating getting sick a couple of times a year. In addition, asthma, which has paralleled the sealing of homes since the 1950s, the increase in asthma, the increase in allergenic rhinitis, the increase in eczema, these have followed very closely with how we've sealed up our homes and allowed substances within our homes that we don't know the direct cause and effect, but for sure we've been paying a price by not ventilating our homes very well. And this cost right now is about 60 billion. Yes,
Hi,
Brett?
can you just reiterate? I want to make sure I heard the word eczema, like the skin rash.
Yes, and I don't know if I have that reference in this reference list, but that comes from Professor Bjarne Olesen, who has a number of papers. He's a faculty member at the Danish Technological University, the leading center on air quality and human health and ventilation in buildings. But I'll see if I can look it up and that we can post that with this material, because it's a very interesting plot that he's made.
Thank you.
Yeah, you know, eczema is a inflammation type of illness that it seems to have links in the same way that asthma and allergies have been increasing to whatever it is that we've been putting ourselves in within our environment. And then the big dog as far as value, but you know, there's not really a good meter that you attach to a human, but we estimate now about 10% decrease of human cognition by the elevated levels of CO2 and associated VOCs at typical ventilation levels. And you spread that across, say, the US population, and you're at $1.5 trillion. So are we going to do something productive with that extra 10% if we're able to get it back? That's hard to tell, but for sure we're paying a price in our creativity, our ability to focus, our ability to organize information, our ability to think and get things done. As we get ready to make these comparisons, here's just some more field data, just so you can see that this is real. This top plot is a 3-week study monitoring time period of a certified passive house with a high efficiency HRV, no recirculation. So it just simply blows air in at the stated ventilation levels. This is a retired couple that tend to be in their home, and the first week and a half or so they're at home. The second to third week they're gone, and you can see blips where their son would come in and check over the house, and then they return. And basically the house, the room, the main family room where the monitoring was located, it's polluted when they're there and it's not when they're gone. You can see they're not high polluters because CO2 dominates relative to VOC, so there's not furniture off-gassing or other activities elevating VOCs above what might be expected from the human VOC output. And the plot below is a smart ventilation system from our Equinox house. And you can see 4 years or more of data from Equinox house online. But this house, you can see whenever it gets above the 850 part per million threshold that we have set on the smart ventilator for either CO2 or VOCs, it's brought back down before the pollutant levels get much higher. And similar to the top house, CO2 tends to dominate, that it's a low polluting house as far as VOCs, and the main VOCs are human generated as well as cooking. For a comparison, if we take a 90% HRV in a smart ventilator, and this is a difficult comparison because the type of models that many of you may be used to using, things like PHPP or REM rate or other, say, monthly average simulation models, it can't capture the dynamics of the wind increasing and decreasing in speed, the scheduling of people in the house and not in the house. And it takes very detailed simulation modeling in order to capture these events and to see how a smart ventilator will compare with, say, a high performance heat recovery ventilator. And so the comparisons I'm going to show you, and there's much more detail in the reports as far as breaking the energy pieces apart that go with this, as well as describing the computational model. But this is a 5-minute simulation model using January 2010 from the middle of nowhere, where I'm talking from in Urbana, Illinois. And we're comparing this HRV. It's set to, computationally set to operating at the ASHRAE 62.2 ventilation standards for a 2,700 square foot home. And we use average occupancy, so 2.5 occupants in this average new construction home. And case A has 3 air changes per hour at 50, the level that the International Residential Code specifies that should be the target. And also comparing it to a more highly sealed 0.6 ACH 50, the level that passive home, as well as very high performance homes would tend to shoot for. And then home D is a smaller, there's also a home C, which is a different occupancy to show the occupancy effect. But then a home D, a smaller home with 4 occupants, basically a 2-bedroom home with 4 occupants, also operating at what ASHRAE 62.2 would specify. On this slide, it just shows what this January 2010 looks like. So this is hourly data that's then broken into 5-minute chunks for simulating and modeling the change of carbon dioxide concentration, as well as doing the energy supply needed to keep this home comfortable during this month. And what's shown on this slide, it was a very cold month for part of it. It got down to -10, but the average of this month was about 20 degrees, which is basically our normal January average. But in weather, average never actually happens. You're either above it or you're below it. And very rarely, as you can see here, was it ever really at just 20, 22 degrees. The wind is all over the place. You can also see that the wind speed doesn't correlate with the temperature. Sometimes the wind is high when the temperature was high, sometimes it was high when it was cold, and other times it was low. The thing about wind is that whether it's a sealed, very well sealed passive house, a 3 air change per hour, still very well sealed new constructed home, or a 10 ACH infiltration home, is that at 5 mile per hour wind going to 10 mile per hour wind, that's not just a doubling of the infiltration, that's a quadrupling. It goes with the square of the wind speed, the infiltration. So then as you go from 10 miles per hour to 20 miles per hour, it again is 4 times as much infiltration, or 20 miles per hour is 16 times the amount of infiltration as 5 miles per hour. So basically that means that when the wind's not blowing, you're getting nothing. And when the wind is blowing, you're getting a bunch. And this is very, very much an important aspect of how a smart ventilation system works. When the wind is bringing in the air, then you don't need to be ventilating so much, depending on the occupant activities. And when the wind's not blowing, even in a leaky home, that you need fresh air brought in. And this slide, before we look at the comparisons, we see that at about 850 parts per million, a level that we consider a good level to shoot for, that there's about 5 or 6 days with these orange lines that exceed it when the wind speed was so low that even with a leaky home, that it wasn't enough to keep the air quality at a good level. And the energy usage for a 10 ACH home with this type of January month would be about a $250 utility bill based on the heat being supplied to heat up this infiltrated air coming from a high performance mini split heat pump, something like a Mitsubishi or Fujitsu or other brands that you may be familiar with. So as far as comparing an HRV with a smart ventilator, if we have a 3 ACH home, 2,700 square feet, average occupancy 2.5 occupants, this home would be ventilated according to ASHRAE 62.2 with about 120 CFM. And relative to the 2,200 kilowatt hours of energy needed for ventilation related energy in the leaky home we just looked at, this home would reduce that to less than half. So, ventilation and infiltration are very important impacts on energy. This home would be somewhat less than 900 kilowatt hours rather than 2,200. So very beneficial to have this type of heat recovery. You also see that the CO2 concentration in it, because a 3 ACH home has a large amount of air supplied by infiltration, that it's well below, say, 1,000 or 850 ppm. Now, the same home with a smart ventilation system and the controller for the simulation model, we assume an upper threshold of 1,000 ppm would kick it into a ventilation mode and ventilate until it's brought down to 900 ppm. And the selection of 1,000 ppm for the upper threshold is based on that being equivalent to roughly where ASHRAE standards would have a home ventilated to. And so it's part of trying to get an apples to apples comparison. But this home, when it's well below 1,000 ppm, it's essentially getting fresh air from infiltration. And when it hits 1,000 ppm, the fresh air is ventilation is kicked in, and that's being managed by the smart ventilator unit. This smart ventilator has a heat pump doing energy recovery, and you can read the details on the energy efficiency of the heat pump in ventilation recirculation mode in these reports. But basically, the comparison between these two cases. The smart ventilator keeps the air quality maintained where the threshold's set or better, and it reduces the energy associated with maintaining air quality about 30% less than the previous case with constant ventilation flow. That energy difference about 250 kilowatt hours, or about $30 per month. Now, home B, in which we seal the home to 0.6 ACH rather than 3 ACH with the 90% HRV, this home, it elevates some in carbon dioxide, but it's still well below, say, the 1,000 ppm level. And there's a significant drop from about 900 kilowatt hours in the home with 3 ACH and a 90% HRV to about 430 kilowatt hours in this home. So sealing a home up has a substantial benefit in further reducing energy from about $90 per month to about $45, $50 per month. And it's as a whole, keeping the air quality reasonable. When we look at the smart ventilated home, when it's sealed to this level, now most of the air brought in is coming through the smart ventilator. There's a lot of noise there, and if you look at the 5-minute detail, you would see the ventilator turning on and turning off, bringing it down to 900, coasting back up to 1,000. But basically, this is saying that by sealing it to 0.6 ACH 50, as in a passive home, that now you're managing the fresh air. It's coming from somewhere that you know, outside the house, through a filter and brought into your house, rather than being dominated by air that's coming through the walls or through flue vents or other places into the home. Now, relative to the HRV under similar conditions, the smart ventilation would reduce the energy by 40% to the comparative 90% HRV. While it's a bigger percentage, it's a smaller energy difference, so it's maybe about a $20 for this cold month of energy difference. And again, the breakdown of this is there's about 4 or 5 components to the electrical energy that make up this value, and these are brought out in the report. Finally, home D, which is a 1,000 square foot home with 4 people, basically a 2-bedroom home. If that's operated at ASHRAE 62.2, you can see that, and well sealed, 0.6 ACH, you can see that it's running at about 1,300 parts per million of CO2 and then equivalent VOCs, higher than where we'd like it to have. High enough where it is impacting the health of its occupants, if not just being more odorous. And the energy, about 201 kilowatt hours, so very low energy, maybe $25 for the ventilation related energy in that. With this is smart ventilated and held at 1,000 ppm, and again, the 5-minute data, you see more detail between 1,000 and 900 as it's switching into ventilation and recirculation. But it would increase the energy of the smart ventilated in order to hold it at this better level of air quality. What this means occupant-wise is that even though it has maybe 120 kilowatt hours more of energy, this comes down to about 12 cents per person per day. And that's, to us, a small price to pay for health. Moving on to smart ventilation, and in smart ventilation, I just want to make a couple of primary points regarding the need to make sure that even though you're delivering a proper amount of air to a home, that it's very, very important it's distributed properly. This is actually a conventional home, a home that was built in the 1950s that we monitored, and we placed 3 monitoring stations in the family room, the living room, and then a child's bedroom. It's about an 1,800 square foot home. And even though we didn't do a blower door from these pollutant traces, just like a tracer gas study. We can see that this home it's reasonably well sealed for its age. It's about a 5 ACH at 50 blower door type infiltration level. It's radiant heated, so it's different from homes with central heating. With radiant heating, then the child's bedroom, where two of the kids sleep, when they go to bed, there's a sharp increase in pollutant level. And so this gray line, which is the children's bedroom, you can see how when the children go to bed, it goes almost vertical. Within a matter of 1 to 2 hours, it goes from being, say, at about 1,000 parts per million up to 2,000 parts per million. The parents would open the door at about 9 o'clock once the kids are asleep, and you can see that the pollutant levels tend to level off. But this is a very, very poor air quality room, and it definitely impacts sleeping. So here's a home with no recirculation, but one that's actually kind of on the leaky side. When we consider the type of ventilation that we're seeing in new homes, in which we simply deliver air and then we extract air, but without recirculation, what we call one and done ventilation. When you subdivide, say, 50 CFM or 100 CFM of air among 5, 6, 8 rooms, dividing 100 CFM by 5, maybe 20 CFM, if everybody's over in this one room, it's only getting 20 CFM. That is absolutely not enough fresh air for about any level of occupancy. And then these other rooms that are getting fresh air, and then as it works their way out of those rooms and goes to the exhaust, they may not be touching a human. And so in our thinking, this would be a home that might have, say, 20% ventilation efficiency. Only 20% of the fresh air brought in is benefiting the occupants, but it's not keeping the air quality good, even though it may be bringing it in at a level that keeps the average air quality good. In order to explore this more, we look at some simulation results. And in this case, we're going to put in an occupancy schedule. The previous simulation results on ventilation as a whole, we just fixed the occupancy without an hourly schedule. But here we're going to look at a schedule where people are moving around the house and are in the house part of the time and not in the house. So this is our 2,700 square foot home, well sealed, 0.6 ACH at 10. We'll assume 5 occupants, basically a 4-bedroom home. And these occupants are out of the house for about 8 hours a day. They're sleeping from 10 at night until 6 in the morning with a metabolic rate of about 0.7, which gives us the carbon dioxide generation rate. When they get up in the morning between exercising, maybe cleaning, scurrying around, cooking, doing various activities, just giving them a metabolic rate of 2. They're out of the house for 8 hours. They're back in the house, again, fair amount of activity, and then maybe quieting down from 7 to 10 with a metabolic rate of 1.3. When we look at the air quality in the rooms, and this house would have 120 CFM of ventilation airflow. And if we assume half of that goes into a main living area, say living, kitchen, dining area, 20 CFM into the master bedroom, and then 10 CFM for the other 3 bedrooms plus 10 CFM to some other room like a den or an office. You can see that the gray line, which is the main, say, family room, when everybody is in that room in the morning and then in the afternoon when they return home, that it's exceeding, say, 1,000 parts per million regularly. The yellow line, which is the air quality in the bedrooms, it's low when people aren't in the room, but as soon as they go in the room, as we saw within the other slide, it starts to exceed 1,000 parts per million. You'll see a similar case in our report where we take the 120 CFM and divide it up differently. We add a bit more of that to the main room and subtract more of that from the bedrooms. And it's like squeezing Jello. Now the bedrooms are going to have poor air quality, as well as the main room, but not quite as bad as shown here. Now, if this house were fully mixed by a lot of recirculation or no walls, the brown line shows you that in general, on average, there is enough air being brought in. But where people are, when they're there, it's not good air quality. The red line up above, this shows what happens in a bedroom where, say, somebody is sick. And if you're bringing 10 CFM of air into that bedroom and somebody's occupying it for 24 hours a day, and the reason it's moving around is it's relative to the wind and the infiltration on this home. And so that's what's moving that around with this 5-minute simulation. But the air quality is at a very poor level. This slide, and there's more detail in the report, but we can predict the probability that you're going to get sick when you enter a room with a certain level of carbon dioxide, because it is a surrogate for the amount of germs that are also in the air. And if you're in that room for 4 hours at, say, where that red line is showing at about 1,000, 1,100 ppm, you got about a 20% chance of getting sick. If you're in that room for about 8 hours with somebody ill, you've got about a 30%. Now, as you get to 2,000 to 3,000 parts per million, you're going to get sick. And the flu is transmitted at about 10 times the efficiency of a cold. So it takes much, much less time or much, much higher probability you'll get sick if you enter that room with somebody that's infected. Recirculation is a way to try to break down the barrier of a wall as we compartmentalize our homes, and to try to make it like a single volume, a single level of air quality throughout the space. And we can see the effectiveness of this from this data, which is taken from our Equinox house. The yellow line is the bulk air quality, the parts per million of carbon dioxide going back to the smart ventilation unit. And then the blue line is the main room. It's a living, open living space of living, dining, kitchen. The gray is a small unoccupied bedroom typically, and then the master bedroom is the brownish. And you can see that these things interplay with each other, but recirculation is what's responsible for basically keeping any of these rooms with its occupancy either during the night when the master bedroom moves maybe 100 or so ppm above the bulk average versus the main room when during the day when it's occupied, but that it is a very effective means of keeping it close to the set point band. And in our case, we keep it at 850, and the smart ventilator turns off ventilation when we hit 700. And you can see when the yellow trace hits the red line that the fresh air ventilation occurs. Recirculation is effective up until about 2 hours or so time needed to recirculate the volume of a house. And roughly, as you get above 2,000 to 3,000 square feet, it depends on the ceiling height as well. But for example, a 4,000 square foot home with 200 CFM of airflow, it will take nearly 3 hours in order to turn that over. And you start seeing the differences occur in the different rooms with only recirculation. And it's at that level then that you might consider zoning. And when you consider zoning, basically this means opening and closing dampers, but it's very important to design it so that the dampers are not creating large drops in pressure in the ductwork, which then cost you fan power energy, and that you have an array of sensors that in a sense can detect when you need to ventilate one room or not ventilate another room. And what's shown here are, starting on the left, a battery-free temperature, relative humidity, carbon dioxide sensor that chirps a message back, a wireless message back to the smart ventilator. The wireless switch, which is also battery-free, it's your thumb power that gives it enough energy to chirp a message. So if you go in a bathroom or enter a room, or you're at the kitchen cooking, you press that switch, you can tell the smart ventilator to go into a fresh air mode. And then also circuit sensors, things that you put in line with, say, a light switch or a kitchen recirculation hood that can detect that that circuit is on, and that means that you'd like it to be in fresh air ventilation. So there's a multiple number of ways to configure. This kind of two-zone schematic just shows, for example, a living room kitchen area that's getting 50 CFM of air supply and return, and then say a bedroom bathroom that's getting a similar amount, and where there's no extra call for ventilation to one space or another. But for example, someone's working in the kitchen or a pollutant sensors detected high occupancy in the living room, that this would get augmented, say, up to 75 CFM, while the unoccupied bedroom bathroom might be reduced to 25 CFM. And then the opposite might occur, as well as where both may need enhanced. In that case, a fan speed could be increased. These various sensors for zone control can be layered on each other, that an occupancy sensor, a CO2 sensor, a switch, a circuit sensor, they can all be used in combination to trigger the same type of dampers or various combinations of dampers depending on how the house is configured and what the needs are. These dampers that I'm showing in this schematic, we don't want to ever close a damper and seal off a room. It's important that there's always some level of airflow going through each room. And just to give you kind of a schematic of, let's say, a house that might have 5 nominal zones. And zones are not so well defined as you look from room to room and what you might call one zone or another. And you don't necessarily have the same number of supplies as you have returns. And so each case needs to be looked at for how to most sensibly direct air from one region to another. But in a case like this, where, say, we have zone 1 with a few people in it and unoccupied rooms in the other zones, so we'd want more air going to zone 1 and less to the other zones. And if this, for example, had 200 CFM of airflow, if all of these dampers are fully open, we would be running 40 CFM of air into each of the 5 zones. In order to determine how much air is going into zone 1, we can make use of something called a C value, basically a relation between the airflow and the pressure drop in a section of ductwork. And our reports located on our website on what we call ductology describe these C values in more detail. But something like a damper has a C value characteristic. And the larger the C value, the more flow or less pressure drop it has. And so in the case of a 6-inch damper that's commonly used in these applications, with a fully open damper, a 0-degree damper, we'd have about 1500 for a C value. And if it's closed to about 45 degrees, we'd have about 250 for the C value. And the ratio of these C values determines the flow ratio. And so it's a very simple calculation to make. Depending on the pressure drop in the associated ductwork, there's some additional calculations, but ideally the ductwork is not a large source of pressure drop as well. And so, for example, this case where we'd want to enhance airflow to this one zone and the others to decrease it, if we have this set up with C values, zone 1 would be receiving about 120 cubic feet per minute. while the other zones would be dropped from 40 CFM to about 20 CFM each. And this is with very, very low pressure drop, so that the associated power change on the fans would be quite small. We would expect in this case, for example, to be running maybe about 30 watts for the combined supply and return fans. Finally, we'll end with this local exhaust example. Other ways that zoning, when you implement it, for example, if you're cooking and you'd like to pull a lot of air through the kitchen, maybe you don't change how you're supplying air to the other rooms. And in this example, if you close off, if you reduce the flow coming from, say, bathrooms and laundry rooms and other places, it will enhance the flow coming from the return in the kitchen area. And so something like this active circuit sensor showing near the exhaust hood or the wireless switch, if that's pressed, it would partially close the dampers from the other areas, enhance the airflow from this. And as far as ASHRAE local exhaust standards, this can help you get to, say, 100 CFM for kitchen ventilation. I'm going to leave this, those of you that have attended these webinars before, this concept of pre-ventilation. Our overall goal is not be just thinking in terms of ventilation. We're trying to understand how we improve our health, comfort, and well-being. And this is just a piece of it. And this day and age, we feel is very exciting that we're going to make some pretty significant gains in our health in a way that's going to save a lot of money too. But finally, air quality is very, very expensive in terms of our health, much more valuable than the cost of energy. And we think it's time to focus on designing effective ventilation systems. And smart ventilation systems automatically, they take the worry off you. They're in the background, energy efficiently delivering fresh air when and where you need it. And coupled with smart air distribution through recirculation to get particulates out, to make use of air that's stored in unoccupied areas, and then when needed, layering on zone control, that we have the ability to have much better air quality throughout our homes. And thank you very much. I'm sorry I went over. This is the first time on this webinar, and so any comments on how to trim this thing down are appreciated as you go through the reviews. Thank you.
Hey, great. Thanks, Ty. No worries there. We still got plenty of time for questions. And as those questions are rolling in, just real big thanks to our board of directors, all of our volunteers, everybody who helps support our work and allows us to do what we do. And a huge thanks to our three top tier sponsors, ASHRAE for on the go or in your home or office, solar powered backup battery systems for not if, but when the grid goes down. Mitsubishi Electric for getting to net zero, going all electric, getting net zero using air source heat pump technology that works down to -20 and lower. And then, of course, T-Stud structurally insulated framing systems that save money behind the walls. So yeah, we've got some more time for questions, and as those are coming in here, Ty, I just wanted to real quick. Oh, I see somebody maybe put in part of their question but didn't finish it. So please feel free to finish that off. Anyway, so I wanted to go back to just to some lead or some higher level questions in regarding lead compliance as well, and whether it can work with smart ventilation or work better. And one of the things I'm thinking of now is that a lot of teams are utilizing their ERVs or HRVs to get rid of like bath fans and save money there and vent it, reduce air loss in the house and vent it that way. And then there's also an option in LEED for meeting the prerequisite or even getting the extra ventilation, enhanced ventilation credit, where if you really don't want to do a ducted hood range, you can do at least 5 air changes per hour or more in the kitchen and be able to show that through a calculation. So, I mean, overall, on the top of your head, is this something that smart ventilation can assist? Maybe one of those, maybe not the other?
Yes, in both cases. So let's first, as far as the bathroom, with smart ventilation, and as we've demonstrated now in many, many homes across the country, but that one of the advantages is that you can use it for bathroom ventilation, and that whether you trigger it, the smart ventilator into ventilation mode by a wireless switch, an occupancy sensor, a humidity sensor, but there's various means then to have it ventilate. And even when it's not in ventilation, the circulation, the continuous circulation of air through that space from the recirculation, that's really what dries the bathroom out. And so now where we've got over 8 years of experience, and me personally in a home that that uses this, I can tell you that a heavily used bathroom that's over 8 years of usage, no signs of any mold, paint deterioration, wood deterioration, or things that you would expect to start seeing in a bathroom perhaps over that time. And towels dry out, the bathroom dries out. It's really that lower flow of continuous ventilation that dries it out. 15 minutes of a high rate of ventilation is not going to dry a bathroom out. The moisture has to diffuse through the walls and the tile grout and the towels and textiles in order to dry out, and that just takes continuous airflow over time. As far as, so in answer to that question, smart ventilation for sure manages bathrooms, and we've inspected dozens of homes that use our smart ventilation system, the Serve, and have been in place now for 4 or 5 years. And we're very pleased with what we're seeing, that it's working very, very well. On the kitchen side, the same thing, that the smart ventilation coupled with an effective kitchen hood, and I'll say that right now we have not seen that there are effective kitchen hood ventilators. That somebody needs to do, and perhaps it'll be us, somebody needs to do more basic fluid mechanics on how to capture particulates coming off of a cooking top and protecting the cook, because right now the way, whether it's a few $1,000 custom kitchen hood or a inexpensive one you pick up at a big box store, they are just not pulling the fumes away from the cook in an effective manner. And that's regardless of whether it's a recirculating type or an exhaust type. Perhaps there are some, and if some of the audience knows of some, I'd appreciate any information you might have on some. But our thought is that a kitchen ventilation hood, and as the folks at Lawrence Berkeley National Lab who have studied this more than anyone as far as cooking particulates, as well as the poor job that various types of kitchen hoods do on capturing particulates and fumes. But to us, it should form kind of an air curtain, so that if it's a recirculating hood, which we would tend to favor, that it's pulling the particulates in with a good high efficiency filter, and then it's redirecting that air back down toward the stove and cooktop in a way that, like air curtains in other applications, that's shielding the cook from the particulates that it's going in, so it's not disturbing the cooking process. You don't want to be cooling down things that you're trying to cook as well. And so there's some very sophisticated engineering that's needed and research in order to develop that. But in general, The smart ventilation system, through just its own detection with pollutant sensors as well as localized sensors and switches, that these can manage the air quality in that space. And if it needs to be increased, zone dampering then can be used to bring up that level of local ventilation.
Great, thanks, Ty. So a question here, I thought that most ventilation designs don't have return ducts from bathrooms due to odor concern. Are you recommending direct returns?
So as far as the bathroom return, it will go through the smart ventilator. And typically if somebody's in the bathroom, they either hit the wireless switch, or if they have like a circuit sensor or an occupancy sensor, the ventilation system would just switch into fresh air mode, which means what's going from the bathroom goes through the ventilator and then is exhausted. But the real reason for ventilation, the requirement for ventilation in bathrooms, it's a moisture requirement. If you go back to the development of bathroom ventilation, it's a moisture requirement. And as I recall, although I can't give you a specific reference off the top of my head, but baths, rooms with a bathtub or a shower, those required ventilation where, say, just simply a powder room didn't. Now that's changed where any bathroom, and it makes sense to pull air out and to then exhaust it from a toilet space as well as a bath space. But in general, that air is getting exhausted, and that at other times when the exhaust isn't called for, that air is getting recirculated. Now, it may sound like bathrooms today typically aren't recirculating, but in most conventional homes, there's an air conditioning or central air supply going into the bathroom for air conditioning and heating. And as soon as that turns on and blows air into that room, of course, it goes out the door and then into whatever other adjacent rooms, as well as is getting recirculated through the central system. And so as far as the smart ventilation system recirculating, it's really no different than when any other central system is circulating.
If ventilation is drawn in the kitchen, is additional filter going to be needed to capture grease before getting into the serve unit?
Yes. So you definitely want a hood that would have grease screen type filtration. And so like in our case, we take those which are stainless steel type screens as most of you would be familiar with, and put those in the dishwasher periodically to wash them out. But you do want to try to capture that as much as you can right there. And then the air that's getting returned back to the serve unit, that goes through a filter. All return air goes through a filter. And we'd recommend a MERV 13, although you can use as high of a MERV filter rating as you'd like, or as low depending on your respiratory sensitivities. But for sure, you want to try to first capture grease and cooking particulates at that ventilation hood. But as I mentioned, there's a lot of improvement that's needed in the typical ventilation hoods or kitchen hoods that we're seeing these days. And then the air that's getting pulled out of the kitchen for exhausting, that also goes through a filter.
So you're recommending the filter at the hood intake, and then 13 standard filter, and then a third filter on top of that?
No. So yeah, so the air that's then in the kitchen that's getting pulled out, typically it's not going to be greasy. And again, 8 years of seeing a kitchen that, as I've told people, I'm fortunate that my spouse is someone who loves to cook and cook so many different ways of cooking. So our kitchen gets a real workout, and that one of the benefits that we've seen is that cooking odors do not get infused into the house. When you are ventilating and pulling that out, the odors don't have enough time to infuse and start giving your house a characteristic cooking smell. And we don't see any signs of, cooking, say, grease or deposits or things like that around the kitchen. It's no different than what we're used to in any other home that we've lived in.
And the last question before we wrap up, or this is actually about 3 different people asked this question in various different ways, but it's actually, I guess, more of a kind of an ongoing dialogue. But how do we, talk to contractors and HVAC contractors about the importance of why we need to do this? Like, what are some quick overhead takeaways or bullet points we can use to, get them to want to buy into doing smart ventilation?
That hits the nail on the head. We're struggling with that as well, to make this real to people, that we really have suffered over the past, especially 50 to 60 years, as homes have gotten better insulated and sealed. And although we can't smell it, seeing the price that we're paying with our health, and it's so bad, for example, with asthma, that 1 out of every 3 to 4 homes, basically what 10% of the populace, has a respiratory sensitivity. And so I'm hoping that builders and building designers are hearing this enough, just the same as when they're hearing that folks would like stainless steel appliances or granite countertops or other things of that nature, that and I think they are starting to hear it, but we're at an early time where healthy homes is just skyrocketing when you do web searches on it, but where people are trying to figure out what that means as far as keeping a home healthy. And so I think folks like following webinars like this. I know you had one by Professor Shelley Miller not so long ago on particulates and monitoring that her research group has done at the University of Colorado, that this is getting quantitative information out, and that people will be able to use this to go to, say, an architect or a building designer or others in the industry and tell them, this is why I need this. This is where the quantitative information is. It says, I really want to have less than 1,000 parts per million of CO2 in my home, and here's why. But any ideas folks have, please pass them on, because that's why we do these webinars, is for education. So whether somebody finds that what we do, what we manufacture, is something they'd want to use or not. As I said, our mission is helping people feel better, and we've taken this track to try to do that. But we're just at the very, very beginnings of it.
All right, Ty. Well, I appreciate all of your time here today. I appreciate all of you for calling in and joining us here. Make sure to take the survey that's going to pop up here in a second. And for those of you listening on demand in the future to the recorded version, make sure to take that 10-question quiz with an 80% passing rate to get your Con Ed. Ty, right before we wrap up, where can people learn more about everything you're talking about with smart ventilation and contact you if they have more questions?
So at the end of this presentation, there's a number of references listed. So there's a lot of good peer-reviewed literature on these topics, and as you read the reports, those references are cited there. The The reports we've written are a real snore, so if you're having any trouble sleeping, it's perhaps a good cure for that. But there's a lot of information out there, and we need to start getting that transferred to people. And so, but you can reach us here at Build Equinox and read through our reports and contact us anytime for any questions. Thank you very much.